And thank you all for coming, and good morning. So before I get started, I actually want to make sure I give credit where credit's due here. The main author, Kevin Dyer, who did the lion's share of the work, unfortunately was not able to be here. So you all get the second choice author to come present. So apologies ahead of time. So the first thing I want to do is explain the title a little bit because it might not be entirely clear to everybody in the room. So one thing that probably everyone in the room does know is that different countries like China, but also less expected countries like the UK are targeting encrypted traffic for filtering and throttling because they see it as a type of security concern. Well, that might be true in some cases, but the problem is that it hampers censorship-resistant protocols like Tor or Lantern or any number of the other ones, in addition to normal VPN activity. So the question is, how do you try to re-enable this censorship circumvention despite the fact that this type of application layer filtering is happening? Well, in the last couple of years, the answer to that has been you develop a whole bunch of network traffic obfuscation tools. And they're generally speaking, the way that they work is they take in some encrypted data, they do some magic to it that makes it look like some other not so bad data in terms of what the censor is filtering, and it gets by the filter. So pretty simple task. The thing is that it's actually a really, really dense and complicated space at this point in time. So we have three main sort of what I would call areas of or approaches that are being used. So randomization, which basically is trying to get rid of all static signatures in the data, both in the headers and in the statistical properties. You have mimicry-based techniques, which are supposed to be lightweight methods to kind of do the bare minimum to mimic some allowed protocol that would normally make it through the censor's firewall. And then you have tunneling, which are much heavier weight, often a bit slower, but use the full implementation of each of these protocols to tunnel data in some way or another. Now, I'm not going to go into too much of the details of the pluses and minuses of each of these. I will just point out that there's one sort of anomaly on this, which is FTE, which is some work that I had done with these co-authors in the past. And the main distinction there is just that rather than having a fixed and set of features to look at and fixed protocol to try to mimic, FTE allows users to kind of give a format that they want the data to look like, and the data will conform to that format. So make it look like HTTP requests or HTTP responses. The real thing I want to hit on in this slide, though, is that this design space right now is extremely restricted. Meaning that if an adversary learns a new technique for detecting any of these, the entire code base is completely useless. There's no way of updating them. There's limited access to different types of features. So when a paper like the Parrot paper or Cover Your Axe comes out, there's no way to improve on the system to then add new features to try to mimic or to evade detection. And moreover, a lot of these are actually all HTTP based. And really, if we want to do a good job of making censors work, is we should be moving into a lot more broader base of protocols, not just HTTP and Skype, basically. So with that in mind, I just wanted to kind of walk through some of what we would consider some problems that we see that all of these approaches more or less have. These are kind of like a list of requirements that we see that we would need to hit in our next generation system. And so those include being programmable, so the idea that we can in fact update quickly and adapt quickly when a censor makes a change to detection. The ability to do multiple levels of features, so not just looking at a packet or a message level feature, but also being able to simultaneously do connection level, session level, and so on, arbitrary levels of feature that we want to be looking at, which is exactly what the Parrot paper kind of targeted. And then, of course, stateful protocols to enable this sort of broader environment of mimicry and and other randomization protocols. And then, based on what we've seen in the literature so far, it's obviously very important that we need to somehow address traffic analysis, we need to somehow address active probing, and something that actually is not really talked about too much in the literature, which is active attackers, right? So attackers who want to go and flip bits on your data as it goes through between your client and server. So, and a key example of that is an HTTP proxy. If you throw any sort of commodity HTTP proxy between any of the existing systems, maybe except for one or two from that previous page, they will all fail for various reasons that we'll talk about a little bit later on in the talk. So here is our really grand aspirational view for Marionette. You know, I think we did a pretty good job of hitting it, but there are certainly probably a few weak spots that we need to tie up. But generally, our goal is we want to create a unified and completely programmable system to help people explore the design space of obfuscation technologies, to be able to move around in terms of the depth of the features that they're using or the types of protocols they're using, or even combining multiple different types of protocols into a single specification for how the system would work. And of course, we want to do this efficiently, right? We don't want this to have huge amounts of overhead while we're doing it. So here's a sort of brief architectural overview of what Marionette looks like under the hood. Like most of these other systems, we work in a sort of SOX client, SOX proxy setting. The Marionette client takes in data, passes it through the system where various changes are made to the actual data, it gets sent across, and then all those changes are undone on the opposite end to get the data to its intended destination. In our context, models are actually one of the core concepts, and we'll definitely go into it in more detail in a short while. But these models are, you can essentially think of them as controlling what exactly is being put out onto the observable channel at any given moment. So it can control the sequences and the types of messages that are being sent over these channels. We also have sort of a neat little feature where, in order to ensure that these models can be dependent on one another, so that if you have multiple connections, there are dependencies that can be modeled there, we have this global and local key value store that's shared among those models. Won't talk too much detail about that, but if you're interested, definitely take a look at our code, which I'll give a link to at the end. Now, we have those models, you have to somehow define them in some reasonable way, and we do this with a custom domain-specific language, which basically specifies the structure and how the models operate, and then what actions they take as they move through the structure. This driver is actually pretty interesting because, and there are some interesting parallels here between what we're doing and maybe network traffic generation or simulation design, right? So this driver is essentially very similar to what you would see in a simulator. Just it's an event loop that will ensure that each of the models continues working through each of its states and is producing the actions as we'd expect. And then, meanwhile, on the other side, once the data gets over to the server, it needs to somehow figure out how to take the data from some arbitrary number of TCP streams or other connections and how to assign it to a model in order for it to be decoded and decrypted and then sent on to its eventual destination. And then finally, I mentioned that these models can sort of perform different types of actions, and these actions are going to be defined as these reusable plugins. And again, we'll talk about all of these, or at least most of the important ones in detail, just a second. So first, let's go through the models. So the models themselves are inspired by what's been known as probabilistic input-output automata. The only thing that's really important to understand here is the probabilistic component, and that the input-output means that we can essentially perform actions onto external channels or read from external channels as a result of traversing any of these transitions in this model. And so on the lower left-hand corner here, you see basically a little example of what we call an action block is. So once, let's say, the driver for the client decides I'm going to go through and make the transition to the get state, it will look down into the action block and say, all right, well, what action should I be performing in this send get action block? And it says, basically the client needs to send using format transforming encryption, something that looks like a get message that's got some size. It's going to send about 1,024 bytes of size embedded in it. So what we get out of this, obviously, without really being too obvious, is that we get state, right? We get to now create different types of protocols like FTP or SMTP that by definition require very precise sequencing of packets and messages, and we can actually have different types of relationships among those, including probabilistic ones, which we'll again touch on in a second. Another interesting feature here is that with these action blocks and with the use of these plugins, we can actually do pretty cool things with the models themselves, right? So we're not just talking about a single model for HTTP. Now consider we've created a higher level model that somehow describes web browsing, right? So web browsing is some combination of DNS queries and HTTP requests and responses. And what we can do is by using a spawn functionality as an action, we can basically say, well, when you start, you start your web browsing model, you begin your walk through it. Oh, hey, we decided we're going to start up an HTTP connection. Let's spawn off a completely separate HTTP model, just like the one we saw in the previous slide, that will accomplish that one goal of mimicking the activity in that one connection, right? So now what we actually get is composition hierarchically gets us different levels of specificity in our, or abstraction in our features that we're controlling. So at this top level, we're controlling features of web browsing, for some definition of web browsing, whereas at the lower level, we're controlling features of individual DNS queries or HTTP sessions. Another interesting bit that comes out of using these input-output automata with action blocks is that we actually can use the outputs or the outcomes of the action blocks themselves to determine whether or not we're getting valid messages. So basically built into each of these state transitions, we basically have a predefined set of things. So in our send-get example that we had earlier, we were looking for a very precisely formatted FTE message in the format of a HTTP GET request. If we don't get that, if we are unable to decode that message or parse it or decrypt it after it's been decoded, then something has gone wrong. And now that could either be some miscommunication between the client and server, which is relatively difficult to do given our record layer, or it could be an active probing attack, for instance. And once we get one of those active probes and we start to see failures in our action blocks, we can basically move over to an error transition. And this error transition can do all of the same types of actions, but it can be done in such a way that we're trying to recover or respond to these active probes. So I have just an example here of this request error thing where we just output an Apache banner, for instance, if we get an unexpected message coming in. But you can easily imagine that by using the hierarchical composition that I just showed you, instead of just outputting a single string, you actually run a different model whose entire purpose is just to fool active probing. And then finally, what I wanted to point out here was there's also some nice properties, basically the probabilistic properties of this automata also give us the ability to control different types of traffic features. And this was kind of hinted at a little bit earlier when I showed the model for web browsing, right? Where we can kind of control how often DNS queries are made versus HTTP requests and their semantics. Well, in this particular case, we can actually control the number of concurrent HTTP TCP sessions that are running HTTP in them. So basically by encoding that distribution directly into the model itself, we are able to get this nice sort of traffic analysis resistant feature that we can use. Now, I will make the one note that there are other ways in which we can also include and deal with traffic analysis, in particular by using plugins, which I'll talk about in a slide or two. But this is just to show some of the flexibility of what we can accomplish with the composition of multiple layers of these different models, each of which being able to control its own set of features probabilistically. So now the question becomes, all right, so we have these models, they can do some pretty cool things. How exactly do we specify them, and how easy is it to do that? And we tried to make it relatively simple with this domain-specific language. Basically what ends up happening here is you create a model file using the syntax I have described here, and this model file is more or less just a text file. So what that means is it's easy to update. It's easy to have a large library of them on the client or on the server so that you can quickly jump from, say, using HTTP in a certain way to using it in a different way to using FTP or SMTP. And this is exactly the type of flexibility and efficiency that we wanted when we were talking about programmability in the beginning. So just to briefly walk through here, this first line more or less is just helping us set up what the properties of that channel that I had talked about, that logical channel. So whether or not it should be expected to be a reliable TCP connection or a UDP connection or any number of other connection-related properties. Then we move on to actually defining the structure of the model itself, which is basically just defined by producing one line for each transition. And then we assign each of those transitions to reusable action blocks, which are named. And then, of course, there's ways of basically specifying whether or not that particular line or transition is an error line, which I had talked about before, an error transition, or whether or not you should assign a probability to it and actually use it as part of your normal generative process. And then finally, these last bits are actually really close to what I had shown in the previous couple slides, but really what we're saying here is we want to have a reusable action block, kind of like a function, that gives us the ability to specify which party should do what activity, right? And that activity, like I had said earlier, is completely controlled by plugins. So now what are these plugins? This is kind of the last piece before I dive into some of the case studies. Well, plugins are really just reusable functions, right? So this is where, if anywhere, this is where the heavy code is, right? However, the whole purpose of plugins is that they're supposed to be extremely reusable, meaning that we make the plugin once and then dozens and dozens and dozens of other libraries should be able to, or sorry, not libraries, but dozens of other models should be able to all use that same plugin. So here's just a couple of examples we saw throughout the presentation so far, but a couple of things to keep in mind. So for like spawning extra models, we have the ability to do blocking or asynchronous running of those models. So you can actually spawn off 20 HTTP connections all doing their own thing across their own channels, and then the higher level model can just continue working on as it would have anyway if we have that in asynchronous mode. Another thing to point out is this sleep method, which would basically help you control different types of timing features. And this actually demonstrates you a different way you can embed some traffic analysis resistance in a different way, right? So instead of doing it directly in the model itself, here we can basically create a plugin whose parameter, one of whose parameters is a sleep distribution over basically how much time should you be sleeping and what's the distribution over that time. And this also can be done in a blocking or non-blocking way. So there's a lot of flexibility, a lot of options here for us in terms of what we can accomplish with these reusable functions simply by putting them into these action blocks in the models. There is one slight digression I want to make in here, which is template grammars. It's a very specific type of plugin that we made for this project. I'm not going to get into too many details about it, but the gist of it is for a lot of, especially for FTE, but for a lot of different obfuscation technologies, if you flip one bit, the whole ciphertext is kind of hosed in some way, right? What we want to do, especially if we want to be able to get through HTTP proxies, is make this more resilient, be able to be more picky and choosy about where we're going to end up putting or embedding our data into these different messages. And so the general idea is that we have this probabilistic context-free grammar, and it's actually going to output or generate templates. So a template here is more or less, it's almost a fully qualified final string in the language, but with one difference. That is that at the bottom here you see these two gamma notations, gamma date and gamma cookie. Basically those are what we would call placeholders. So when they get output as terminals from this PCFG, we're basically going to end up calling the proper handler function for those terminals. So meaning that, as the template on the right side here indicates, for the date field, we're going to end up basically calling a function that's going to get us a properly formatted date string that's current. And for the cookie field, it's going to do an FTE encoding of a cookie, basically. But you can do this for many different things, and it's actually particularly helpful when, for instance, for a lot of HTTP proxies, they require you to have correct content length headers, right? And so this is a perfect way to do content length because once the message is fully formed, you can go back and then run the handler for content length, and it will fill in the proper length of bytes, right? So just little things that are very helpful and useful in coming up with more flexible messages. All right, so now into the case studies. This is going to be relatively brief. There's a lot of case studies. First thing I want to point out is some of the what I would probably call adversaries here, which is basically DPI all the way on the left with message content, stateful behavior, which is closer to like the proxy traversal case, and some of the protocol compliance stuff. Multi-layers, which is dependencies between different TCP connections, traffic statistics, and obviously active probing. Now, these weren't chosen completely arbitrarily. They are definitely inspired by what's currently sort of known in both practice and in the literature in terms of what the attack potentials are. But the bottom line is that we don't have a rigorous adversarial model for this system, partly because I don't think the space itself of obfuscation has a good adversarial model on its own. So this is our sort of best effort towards getting us to a strong evaluation of the different features and how our system can adapt to different types of adversaries. So obviously there's a lot of different case studies here. I'm only going to be talking about the proxy traversal and the traffic analysis ones very briefly. But the one thing that I did want to point out was the variety of protocols that we were able to accomplish. So some of these have never even been considered before in the obfuscation literature, like POP3 or FTP. We're actually able to at least hit one of our goals, which is to start to expand and broaden the set of protocols that are available. We're also doing it relatively efficiently. Now you'll see there's a pretty big discrepancy in some of these numbers, which I'll talk about later, but the gist is that the system itself is super efficient, and the numbers that we get are really dependent on what the requirements or constraints of the model that's being run are. All right, so for proxy traversal. So I alluded earlier that basically HTTP proxies will kill most or all obfuscation systems, mostly because they can change headers, but also because they can do neat little things like multiplex TCP streams. So 3 HTTP streams come in, 1 HTTP stream comes out with everybody's requests and responses in it, which makes it difficult for the server to disambiguate which message in that TCP stream belongs to which model. And so just very briefly, in order to handle the header modification issue, we basically take that template grammar idea that we have, and we very carefully place our embedded information into fields that we know for a fact that the proxy cannot change, like URL or cookie. We also do some validation checking, so for content length, like I said, there are some requirements there as well. And then to handle multiplexing, we actually use this broker technology that I talked about much earlier in the talk, which really lets us basically figure out which model to send the data to, even if we have multiple models running. So just obligatory results slide. We have some pretty good downstream bandwidth, but upstream is kind of iffy, mostly because of the limited spaces in which we're able to embed information into those upstream GET requests. So I have traffic analysis, but I only have like a minute to go, so I want to skip ahead, so apologies for that. So one last thing about the bottlenecks. So we did see this big drastic difference here, right? And the question is that Marionette or is that actually something in the model itself? And the best that we could do in terms of trying to disambiguate those two things is by looking at the percent of time that is spent blocking for each of these different types of tests. And basically the gist is if you have less time blocking, I mean, you're basically doing a lot more work in Marionette. If you have more time blocking, Marionette's just sitting there doing nothing. And for most cases, Marionette is actually pretty efficient, right? The only case in which it starts to really test Marionette's performance limits is in regex-based DBI, which gives us 68 or 70 megabits per second in both directions. So that's it. I'll wrap up and take any questions that you might have.
Can you talk a little bit about the complexity of some of the automata that you need to construct for fairly complex protocols, something like Skype, to get around the parroting problem?
So Skype, we haven't really looked at too closely. I can imagine that is potentially very complex, though. I mean, and so I point people to go take a look at GitHub. We have all of our formats in there, so you can see specifically what what we're actually doing, but. In general, for the formats that we have looked at, so POP3 and FTP, and even the ones that have quite a bit of state, they're not necessarily complex, right? So actually, FTP is basically a string of states and like a little loop at the end, and that's it. So I would imagine actually for a good number of protocols, it's going to end up being simpler than you might imagine to do just the basic protocols. Now, once you move to higher level things like, oh, I want to try to represent web browsing, that's where there's open questions, right? And like I say on the slide, the limitations are definitely not fully understood by us at this moment in terms of what we can produce and what we can produce efficiently and safely.
Hi, thanks for the talk. So with FTE, the way you program it is you just provide a new regex, basically. Mm-hmm. And with this, the way you program it is you provide these new domain-specific language files. Mm-hmm. And in some sense, in kind of today's pluggable transport system, the way you program it is you provide a new Python file, mm-hmm. right? Because pluggable transports today often written in Python. So, I mean, at a conceptual level, what's the difference between providing a new domain-specific language and providing a new Python language for, like, when you want to update your pluggable transport?
Yeah, I think it's, well, from my perspective at least, I won't speak for all of my co-authors, but from my perspective, it's the level of complexity that's potentially required and the level of sort of auditing required. So, like, a new Python file comes out, which technically, I mean, in the simplest of cases, it's a single Python file. But if you wanted to update an existing pluggable transport, it's one or more Python files that have gone through a very long software development process before that. With this, it's, at least on the surface, from my perspective, simpler to more or less rejigger a model than it is to build a completely brand new Python system.
Well, if you're building a new, like, the equivalent I would think of like completely replacing the Python thing with something that's gone through a development process would be like suddenly you want to support Skype, for example, as Micah said, and you didn't before, and there's going to be some software development cycle even in your domain-specific language.
Sure.
Right? And so conceptually, it seems similar. I totally buy that the set of things that can go wrong is smaller if your language is less expressive.
Yeah, I'd also probably just say that I think it it focuses down the required sort of where you need to put your brain power, right? So rather than worrying about coding in Python and all of the things that go around that, here you're really thinking about coding just, it's essentially a very simple coding language just for obfuscation, right? So you have very well-known elements that you can plug together in pretty simple ways, I think. So yeah, I see where you're coming from that perspective, but I think that the cognitive load level is at least a little bit lower for the models than it is for like a full-blown Python system.
Okay, great.
Okay, let's thank Scott one more time.